Okay, let's talk a bit more about titrations. Um, so let's talk about the titration of a strong base with a strong acid. So if we have an acid-base titration, this is going to be the titration where the reaction between the analyte and the titrant is the acid-base reaction. You can do titrations of really any reaction. It just needs to be fast enough for you to reasonably be able to do in a lab. And it needs to have some property you can monitor. As you learned from this last lab we did, where it's an indirect reaction of a reaction. um, so the acid-base titration curves can be used to deduce the quantities of your reagents, the pKa values of the acidic and basic substances. Your goal is actually to construct a graph to show how pH changes with titrant added. So if we consider this titration right here, 50 milliliters of these two concentrations of a strong base and a strong acid, we write this chemical equation between the titrant and analyte. And notice that we can actually take the K plus and the Br minus, and we can just say, hey, they're spectators, they're not going to accomplish anything, and remove those from our reaction. You guys remember your gross then net charge reactions? So you had those net change reactions in general chemistry. That's what we're looking at here. This is the net change reaction. So the H plus from the acid, strong acid, the OH minus from the strong base, that's going to give us water. We'll also have KBr salt in there, but it doesn't accomplish anything, it doesn't do anything. They're spectator ions. Okay? So we can ignore this. Now, for this reaction right here, notice this is actually the same reaction as the autoionization of water, isn't it? And so it's just the reverse autoionization of water. So it's 1 over Kw, which would be 10 to the 14th power. And so what is the equilibrium constant for a strong acid, strong base? 10 to the negative 10 to the 14th, right? And so that is the cutoff, the definition of a strong acid. Okay? Where does the aqueous pH scale stop? 14. Why does it stop there? Because that's the maximum value we can get. Okay? Okay, so we calculate the volume needed to reach the equivalence point, and the VE would actually be 0.01 liters. We use that with the HBr concentration, and we get here that we would end up using 10 milliliters of that HBr. So when 10 milliliters of HBr has been added, the titration would be complete. Okay. Everybody understands why that's 10 milliliters instead of it being 50 or something? Because that's 0.2, right? So it's a fifth, the concentration. Yeah. Okay, now, there's going to be 3 regions to a strong acid, strong base titration curve. You're going to be tempted, and even I do it sometimes, to call this first region the buffer region, but it's not really a buffer region in the case of a strong acid, strong base, because you're never going to establish a buffer. Okay, you don't have any weak acid, weak base to establish the buffer with. So before the VE, that's this first region that we would normally see the buffer region in. But this is before the VE for a strong acid, strong base. You can actually use that same terminology for weak acids, by the way. So before the VE. That's going to have, in this case, excess unreacted OH minus present because we're actually starting with the base. Okay? And so that's going to have excess OH minus. The pH is going to be determined just by the excess OH minus concentration. Whatever that concentration it is the pH. At VE, we're going to have just enough H plus to sufficiently react all our OH minus to water. And so that's just going to be the same pH, which would be 10 to the negative 7 for both those concentrations, right? That's just going to be the Kw for water. Okay? And for strong acid, strong bases, you always end up with a VE, an equivalence point, that's pH is 7. Because it's going to be set by your water. What would happen if I changed that temperature, by the way? I'd change this. So whatever the, remember how we had that little chart of the KWs at different temperatures? Yeah, whatever that is for that temperature, that is your inflection point. That is your VE. That is your equivalence point for a strong acid, strong base. Okay. Okay, after VE, we're going to have excess H+, and so your H+ concentration, your pH, is just directly done by that excess strong acid, excess H+ concentration. That's all that determines that. This is actually the 3 regions and data for those 3 regions, and as you can see again, we'll have excess OH that gets slowly used up, and those determine our pHs here. Okay? And then we get to the equivalence point, and that's going to be pH 7 for strong acid, strong base, because they'll fully dissociate and fully react with each other. Okay? And then you have region 3, which is where you have excess H+, right? Right. So, when you did this in general chemistry, okay, before that equivalence point, when you have 3 milliliters of HBr, you've added those, the total volume would be 53 milliliters. The HBr is consumed by the NaOH. It'll leave excess NaOH. So the moles of HBr added would have been this right here. You would have calculated the moles here in your general chemistry problem. You would have calculated out the moles of NaOH. You would have subtracted the moles of HBr from the moles of NaOH. That would have given you this. And then you would have taken and divided that number by your 53 milliliters, right? We did these in millimoles, so our millis will cancel in both places. And that would have given you your molarity, right? Take the negative log of that value once you have that. Kw divided by the OH minus concentration right there. Take the negative log of that, and that gives you pH 12.12. There's a faster way to do it. We can sum it up in this equation here. So if you have that equation, you can do a streamlined calculation method. You'll notice that's the same equation I had shown you before with the dilution factors in it. So this is the fraction of OH minus remaining times the initial concentration of your OH minus times the dilution factor. Everybody say okay? And so now instead of using this and having 4 lines of equations that are about the same length as what we just did, we can do this in 1 line of equation. That's like, what, fifth the length, fifth the work. Okay, again, that will give us our OH minus concentration. We still have to take the Kw divided by that, negative log of that value. That's going to give us our pH. Okay, I'm actually at past time. You all have a great day. We'll start up here next time. I'll have to go fairly quickly on this. Hopefully you guys are more rested.